the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video for linear algebra students who are going through coordinate mappings or coordinate systems in their linear algebra course. In this video specifically, we're just going to talk about coordinate mapping, which really will feel very similar to all previous videos in this specific series. There are two theorems in this video, neither of which I'm going to prove, mainly because their proofs are usually in a linear algebra textbook, but there's one large-ish problem, and we'll go through and do all parts of that problem. But before we do, let's go ahead and read off this theorem right here. And by the way, if you're watching the videos in the order that I've posted or recorded them, then you know that we've gone through and talked about uniqueness and isomorphisms. We've talked about coordinates in Rn relative to bases. We've talked about coordinates in Rn relative to bases in Rn. And we just finished a conversation about the change of coordinates matrix. In the last two videos, I've really tried to emphasize that at that time we were only working with mappings from Rn to Rn. But in this video, we'll step back into mappings from an arbitrary vector space into Rn. So let B be this set of vectors, and let that be a basis for an arbitrary, possibly abstract vector space V. Then the coordinate mapping x to the B coordinate vector of x is a one-to-one linear transformation from V onto Rn. And really this falls out actually from one of the final theorems we had in the previous video, at least in Rn, because we know we have a change of coordinates matrix if you have a mapping from Rn to Rn, and that change of coordinates matrix is invertible, and therefore by the invertible matrix theorem, as a linear transformation, it is one-to-one and onto. So that's just a verbal justification of this theorem. However, I want to be clear here and just note that I'm not going to use this theorem in this video. I'm just presenting it just to tie up some loose ends. Likewise, this theorem is presented just for completeness. If we have some vectors in our arbitrary or our abstract vector space, and if C1 through Cp are the weights that we can apply to those vectors, then the coordinate vector of the linear combination of those vectors is a linear combination of the coordinate vectors. This is actually a property of just working with matrices, to be honest with you, and linear transformations. So not a huge deal. You can again probably read that 1 or 2 line proof in your text. But the entire point of this video is to work with this problem right here. The standard basis for P sub 2 is 1t t squared. Write the change of coordinates matrix P sub B for this basis. Well, first of all, we have to find a nice set of vectors in R cubed to represent these vectors that are not from our nice little space called R cubed. So I am going to go ahead and say that a vector that represents that will be 1, 0, 0. A vector that represents t will be 0, 1, 0. And finally, a vector that represents t squared is 0, 0, 1. That is, the first entry of any of these vectors represents t to the 0th power, the second entry represents t to the first, and the third entry represents t squared. If those are the basis vectors in our coordinate system, then the change of coordinates matrix is just going to be the matrix with those vectors as its columns, which is the 3x3 identity matrix. Very, very nice. Now write a standard vector that can be found in P sub 2. Remember, P sub 2 is the vector space of polynomials of degree 2 or less. A standard vector in that space is this second degree polynomial right here. Notice I'm not using matrix notation or vector notation there, like a column vector notation, because they're asking for a standard vector from that set. Now in the part C, they're saying write that in coordinate vector form. And again, if you've been watching my videos in this series, you should notice that this is exactly the same as a previous example up to a certain point. Well, let's multiply that last vector, the b coordinate vector for x, by the change of coordinates matrix. Well, that's just the identity matrix up above. You can see it. So really, that product will just return A0, A1, A2. But remember, the change of coordinates matrix times the b coordinate vector will always return the vector x. Well, the reason why it returns the vector x and the vector x is the same as the b coordinate vector is because our basis that we chose to work with is actually the standard basis for P2. So we literally are saying, hey, change from the standard basis to the standard basis. Well, there's no change when you do that. You're staying within the standard basis. It's sort of like somebody saying, I have this vector in R cubed. It's 1, 2, 3. And I want you to write it in terms of another vector in R cubed, but from the perspective of the standard basis. Well, if you walk in the room and you hand me a vector that's already written in terms of the standard basis, 1, 2, let's just say you said that. Oh, this vector 1, 2, 3 is written in terms of the standard basis. Oh, by the way, please write that in terms of the standard basis. I would say, okay, well, it's just 1, 2, 3. It's literally what just happened here. Finally, part E is just saying use coordinate vectors to show that these polynomials are linearly independent. That means write these as vectors. So I will call this the vector v sub 1. Likewise, this will be v sub 2. And this guy, which bleeds over actually, over here we'll call v sub 3. That's plus, I'm going to write the 6t squared right here just so that I have it in my field of vision. Now we want to use coordinate vectors to showcase that these vectors are linearly independent. To show that these vectors are linearly independent any other way is going to be a bit of a challenge. Those are our coordinate vectors. If you place them in a matrix, knowing full well that it actually doesn't matter which order you place them in. So if v1, v2, v3 are linearly independent, they're linearly independent no matter what order you write them in. So I'm writing them like this for a very special reason. We encountered those three vectors before as the basis for R cubed, or as a basis for R cubed. So just from a previous video, we know that those three vectors must be linearly independent because they were considered as a basis for R cubed. However, if you just weren't certain or you didn't have something to reach back to showcase that these were linearly independent like that, there are a lot of ways now that we can showcase those vectors are linearly independent. One way is, well, if they are linearly independent, that is, each of these columns are linearly independent, then this matrix would be invertible. So as long as the determinant of this matrix is non-zero, the matrix is invertible, and therefore the columns must be linearly independent. I will expand about row 2. And we get a determinant that's not 0, therefore A inverse exists, therefore by the invertible matrix theorem, the columns are linearly independent. That's a really nice way of using material that we've learned recently, or at least in our recent history. Now let's also recall that this set right here is also a basis for P sub 2. Let's use that information to find a coordinate vector of P of t, which is equal to -2 plus 7t plus 2t squared relative to that basis right there. That is, we want to find constants C1, C2, C3 such that, however, since S is our basis, and S is equal to the set 1, 1 plus t, 1 plus 2t plus t squared. I just distributed things out. The change of coordinates matrix is this matrix right here, the matrix where we have essentially created vectors, column vectors out of these statements. Remember, the first row in each column represents t to the 0th, the second row represents t to the 1st, and the third is t to the 2nd. Now this is where I bring it all the way back to the beginning. Remember, our change of coordinates matrix times our b coordinate vector will turn into the vector in our standard view. Remember, the b coordinate vector is the coordinates in terms of this weird basis b. And what we want in this problem is to find out what is this vector p written in that weird basis b, or in this case s. So again, they've handed us the vector p in terms of the standard basis of p sub 2. It's just negative 2, 7, 2. We know the change of coordinates matrix is just the matrix of the brand new basis vectors, and we need to find what this vector is right here, and that's just solving a matrix equation. When we do so, we get that the s coordinate vector for p is negative 7, 3, 2. That is, p, which is the polynomial right here, can be written as follows. It's a pretty nice application where you might want to recenter a polynomial. All right, that's all I have for this video. There's not much else I can do here, so I'll leave it to you. I hope to see you in future videos, and I hope you have a wonderful day. Be a kind human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.